calcium and magnesium. That's mainly what it is, other than, well, I'm getting ahead of myself again. Hardness in water, water is a universal solvent, and it's kind of like your human life. We're all products of every experience that we've had. So water is the same thing. It takes on a little bit of everything that it touches. And when it percolates through soils, it comes in contact with limestone, chalk, dolomite. Let's see here. What is total compensated water hardness? Luann, Tammy, you might hear that. Jeff, sometimes we'll talk about total compensated hardness. You might have heard that through the years. Total compensated water hardness factors in other minerals that affect a water softener's performance. For example, the big one is iron. What we do is the Water Quality Association says that 1 part per million of iron is equivalent to 3 grains per gallon of water hardness. However, at Diamond, we've been, for many years now, we've been using 5 grains per gallon. When we're calculating water hardness, if somebody has 15 grains of hardness and 1 part per million of iron, in many cases you can get by with saying 3. In our area, we say 5, because when you're treating water, you're mixing a science with an art. And we'll find that, like up in other parts of the state, the 3 grains per gallon per iron, per part per million of iron works well. But in our community here, in our area, we have to jack it up to 5. What does hard water do? It causes white scaling. You can see on the end of that faucet. Really what that is it's just dissolved limestone. Its hardness is dissolved rock. It clogs and reduces the lifespan of other plumbing, such as water heaters, reverse osmosis systems, residential through industrial. And it reduces the efficiency of soaps and detergents. And that spreads goes across the whole spectrum from a household to a commercial laundry to a car wash. Well, I jumped there. Decreases RO membrane lifespan. Hardness and soap efficiency. The surfactants used in soap combined with hardness creates what is called soap scum. Some people from the old school refer to it as soap curd. And more soap must be used in hard water to create the same lather to affect an effect as soft water, because soap is used to create soap scum instead of a lather. Now what that means is if you fill a bathtub with hard water, before you can create one bubble, all of the calcium and magnesium that's in the water needs to be coated with soap before the remaining soap can create lather or suds. And when that calcium and magnesium gets coated, it becomes heavy, and it falls out. It clings to the surfaces of your bathtubs, your shower stalls, shower doors. And what you'll see is when you drain the tub, you get that ring of soap scum and soap curd. And that's all it is calcium that's coated with hardness. One little tidbit here is every grain of hardness can increase the amount of chemicals needed by 10%. That's for every grain. So Wisconsin state average is 15 grains per gallon. And this is your some people call this the water cycle. Has everybody seen this before? It's a hydrologic cycle. It's really the pilgrimage of water that it goes through before it goes back out to the ocean. It all starts really with the evaporation of seawater, and it is carried by our wind currents over the land, and it will through rainfall or snowfall, it'll land on the soil, and then it will work its way through the soils into shallow water supplies and over time into deep water supplies. But you also get runoff into your rivers and streams, lakes. And another way, actually 90% of your water that is cycled through our atmosphere is through evaporation, and then the actual approximately 10% is through coming off of plants, and it's not perspiration. It's called
what's that?
The process that's used for. I thought it was on there. And then you've got actually another means that water gets into our system is ice melt and snow melt while the air is still frozen, below freezing. You ever notice a snowbank shrinks and temperature never got above 10? There's actually a process that the water goes through that will actually create itself into a gas, which is a vapor. Hardness and soap efficiency. Let's see here. I just went the wrong way. Yep, measuring hardness. You might hear people refer to it, my hardness is so many milligrams per liter. Some people refer to it as parts per million. It can also be referred to as grains per gallon. And the thing to remember is 1 grain per gallon equals 17.1 milligrams per liter, and the same 17.1 parts per million. Milligrams per liter and parts per million are the exact same thing. So there's really two different ways to explain the bottom column. Hollywood. Measuring hardness. Soft water is less than 1 grain per gallon on a domestic or residential for a household application. People will, like I got a call the other day from a mechanical contractor down in Chicago. They're sizing a system for boilers, and they need to have it less than 1 part per million at all times. And we'll show how we can accomplish that as we move forward here. So this here is a WQA report really calling out the different levels of hardness. You got soft water, which is less than 1 grain per gallon, which once again, remember, is less than 17.1 parts per million. Okay. Our field test kits you guys are using as testing in
Grains per gallon.
Yes. Slightly hard is 1 to 3.5. Moderately hard is 3.5 to 7. Hard water is 7 to 10.5. Very hard is 10.5 grains per gallon and above. Wisconsin state average, once again, is 15 grains per gallon. Softening is the process of removing hardness minerals from the water. Four main methods of removing hardness. We display it here, but in bold letters is what we use is the water softener via the cation exchange resin. The other three techniques are for another presentation. A water softener controls the flow through cation exchange resin. There's really three main parts, which are the main costs to building a system. And you see we highlighted the first is the resin. The second is people refer to it as a mineral tank. Dan and I even talked about it because in water softening we don't call it mineral, but a lot of people do. That goes back to the old days before there was synthetic resins. But these mineral tanks are used for many other applications. You put so many different type of filtration media in it, so we need it called mineral control valve. That's another expense to the equation. The resin. Has everybody grabbed a handful of resin and looked at it? It looks, to the naked eye, I always say it looks kind of like fish eggs under a microscope. You can see that it's a very complex, individual complex beads. Most common exchange resin used for our water softeners consists of beads of cross-linked polystyrene. This is a mouthful. With sulfonic acid functional groups, which really it's just it's a chemically charged polystyrene bead. These functional groups act like exchange sites and are negatively charged and attract positively charged cations: sodium, calcium, magnesium, and potassium. It's kind of like a magnet. Each bead, if you look at the molecular structure of the contains millions of reaction sites. And we have listed here the cations, the most common cations, and what your most common anions are. You don't have to commit these to memory right now, but you will learn it the more you use it. Here's the you'll see SAC resin. That stands for strong acid cation resin. And if you look at the little balls going towards the resin bead, the two blue balls are calcium and the green are sodium. And if you notice, the way it works is for when the blue is attached and the calcium is attached to the resin, it requires two sodium ions to drive off one ion of calcium and magnesium. Okay, let's see here. And the reason that it takes two sodium ions to drive off the calcium ion is because the calcium ion is a much stronger magnet to the resin bead than sodium is. So when we regenerate a softener, we need to run a saturated brine in a concentrated form through the resin and bombard each resin bead with sodium, so that resin can actually let go of that calcium and cling on to sodium ions. Okay? Sodium is released into the water and is sent out to the outlet of the water softener. And a lot of people say, well, gee, I shouldn't drink soft water because we're drinking salt water. Well, that's all relative to the amount of hardness that's in the raw water. And that we'll get to shortly. Regeneration, the softening process can be reversed, but something must be done to overcome the resin's affinity for calcium and magnesium. And once again, that's mentioned in the brine solution in the concentrated form. Excess sodium present in the brine overcomes the resin's stronger affinity for calcium and replaces the calcium and magnesium on the exhausted resin. And here it is. Here's the brine bombarding the resin bead to knock off that calcium. Is that helpful for anybody? You see how that works? The answer to that camera. In the presence of excess sodium and calcium, the magnesium in the presence of excess sodium, calcium and magnesium are replaced with sodium. Calcium, magnesium, and unused sodium chloride are then rinsed to the drain. The mineral tanks, you can see ours are fiberglass. We use it's really a two-ply, so to speak, tank. The outer shell, actually the inner shell is a blow-molded poly inner shell, and it has no rigidity to it. So if you were to stand it up, it would just kind of flop over like a balloon, a weak balloon. So then they take fiberglass roving and the individual strands and they wrap it to give it its rigidity and strength. And inside, you can see we've got the distributor tube, which needs to, it plays a big role in a mineral tank. Let's see here. The key here we talked about is the control valves must be tight. The control valve seal must be tight enough to hold line pressure. We have that happen quite often where it's not. The tanks must be sized to allow resin to backwash correctly. And what do we mean by that? People will see that we have an empty spot above the resin. You see that the open air. And people say, well, why don't you just fill it right tight with resin? The way the water softeners that we build are designed is they're designed to have 50% freeboard space. We need to lift during the backwash cycle. We backwash and lift that resin 50%. If you got 20 inches of resin, we need to deliver enough backwash flow to lift that resin bed by 50%, which is 10 inches. So we need a 30-inch tank to house 20 inches of resin. Okay? Quick tips. Before adding your resin or your gravel, you must install a tank on a level surface. And we talk about that because the smaller tanks that you guys work with the most have self-leveling feet, legs, bases, I guess you call it. But on the larger tanks, they're fixed, and there are shims available, or tank legs available. Do you use them much, Rick?
No.
Okay. Other than you see competitors, they'll take a copper pipe and smash it down and use it as a shim, or even use a wooden shim. It's very unprofessional. It looks like that. You don't want it in your own home. So use one of our feet. Also, this is for our dealers, if you receive a system from us, the control valve is not on it. And on a larger tank, you want to set it in place and identify where the front of the tank is before you fill it. So we ask that the customer put the control valve on and snug it tight, and take a magic marker and mark the front. Then remove that control valve and center the tank so the magic marker, the mark is facing the front, and fill the tank at that time. Because with these larger units, once you fill them, you're not going to move them real easy. And if you do try moving a large, 10 cubic footer or larger that's full, you could end up breaking the bottom of the base.
And most of the times, if there's stickers on the tank, the stickers will align with the front of the tank. So that's a good indication of what side of the tank is the front.
If
there's stickers.
If we put a sticker on it. Inspect the distributor tube. It doesn't happen a lot, but there are times that the distributor gets crushed or damaged. And then, the big one, you see the tape over the distributor tube. Before you fill it, make sure you cover it. Tape the top of that distributor tube. Oops. Go the right way. Yep. Good idea. The water softener controls the flow of water through the cation exchange resin. Let's see around the control valve. The control valve controls the water flow through the softener tank and resin. And there's two main technologies that are used today, really. And one is the piston style, and there's two examples. One is the clack in the top. That's just a 1-inch single control valve that utilizes a piston, and the bottom is a Fleck 3-inch. That's the 3900. Then you've got the flapper style, which is really strictly used by Autotro. Here's a picture of the piston and seals and spacers in a cutout version of the valve. It also shows the drain line, the drain line flow control, which is easily accessed and removed by simply removing that red rubber plastic locking bar. And it just shows the refill and how to access the injector. The bypass assembly allows a water softener to be bypassed so you can service the control. In Wisconsin, it's state code that a means of shutting off the water softener and not interfering with the water supply to the home that's cold. If you don't put a pre-assembled or pre-manufactured bypass assembly on, you have to plumb in a 3-valve bypass, which yesterday you got the experience doing, Todd. The flapper control system is a series of flapper discs that act like switches, turning on and off to direct the water flow. These are referred to as multi-port valves. There's a lot of functions that are going on inside of one control valve by either a shift of a piston or by the turning that cam and opening and closing certain valves. It redirects water through a backwash flow control, or in another position, it'll direct water through an injector. In another position, it'll put it in the service position so you can get soft water. This used to be done when I was a kid. It was offered where you'd have a nest of diaphragm valves. And then there'd be a little separate stager that would fire open valve number 1 and valve number 3 and shut valve number 6 and valve number 7. It was very difficult to troubleshoot and service. This here has made it so much easier. The internal drain line flow control on the residential units and light commercial many light commercial units determines the flow rate for the backwash. and the fast rinse. Okay, and here's a flow diagram. Let's see here. Trying to follow how we did this, the basic construction of the water softener. The control valve controls the flow from inlet, outlet, drain, and brine line. The distributor tube separates treated water or treated from untreated water. Distributes water evenly through the resin. That's critical. You'll notice that we use two different types of distributors. On the smaller tanks we use a basket type with just fine slots in it. And on the larger tanks we use a hub and lateral. And that's because as the tank gets wider, when you draw water, water passes through, and if you have a stack in the middle in a large tank, the water will actually create a V going towards that distributor, and you get a significant amount of the resin that's outside of that V that never gets used. So you actually lose capacity. So by putting the fingers at the bottom, the hub and lateral, when the water passes through it, it goes straight down and it's collected at the bottom of the tank evenly. Brine tank holds the salt and the brine solution for regeneration. Control valve, the flow diagram. You follow the flow. This one shows 6 cycles of operation. So that's service, backwash, brine draw, slow rinse, fast rinse, and refill. And here we go. The top center is when the softener is in service. In service is when it's not regenerating and when you can use water and get soft water. A lot of people will call you, and on a lot of softeners it will say service. Either an arrow is pointing at the word service or the timer says service. And then the service technician gets a call saying, my softener says I need service. Yeah. And then you got to explain, no, it's in service. Okay? So when it does regenerate, the first stage of regeneration is backwash. I think we might have a different picture here. Here we go, the regeneration cycle. The first stage is backwash, where the water is directed through the distributor tube and it is flushed up through the resin, lifting that resin. The desired amount is at 50%. And that's approximately for 10 minutes. And then it goes into brine draw. And you can see the flow changes. The valve shifts and the water flow is directed to go down through the resin slowly, and it's collected by the distributor and sent up through the distributor out to the drain, the red line. And after the brining tank is drawn empty, where the water's all drawn out, it continues into slow rinse. And what this does is it rinses the brine through that resin so it can create the ion exchange process and drive off all those calcium ions. And then it goes into fast rinse, which the water's flowing the same direction, but you want a fast rinse to drive off any excess calcium, any excess chlorides, sodium. But another big reason for fast rinse is to purge the bed. It's to compress the bed and so it's recompacted. So before you put it into service, you need to have that bed compacted so you don't have any hard water channeling through the bed. Final regeneration step is fill, where the control shifts and it puts water back into the brine tank. That is so it can, the water will sit in the brine tank, creating a dissolved brine for the next regeneration, or for the next time the softener regenerates. I just explained this all. Okay, the server position. This is nice to understand. As hard water flows through the resin, the reaction sites on the resin start to get filled up with hardness ions. The resin near the top becomes exhausted first. Over time, the entire resin bed becomes exhausted, and then the system will be unable to produce soft water. And at the time, then it says the softener should be regenerated. Well, that is true. However, let me back up here. We set the softener up so it regenerates before it completely exhausts. Because if you exhaust a water softener completely, it's known as breaking the bed. If you break the bed or completely exhaust the resin bed, one regeneration isn't going to bring it back to full capacity. Okay, so if you go out to a home and they have hard water and have been getting hard water because like even at the cheese factory, the meter's probably plugged, they've been having hard water for 6 weeks. The softener hasn't regenerated. If you go in there and you give it one regeneration, you're not going to bring it back to full capacity. It needs 2 back-to-back regenerations to bring it back to full capacity. If you don't do that, you're going to get another phone call. I explained the backwash. Backwash not only is used to break up any suspended particles that are removed, kind of like a filter would, but it also reclassifies the resin. And I'll make sure we have a slide on the reclassification.
For the fast rinse, yeah.
Pardon me?
For the fast rinse, I guess.
Okay. Then we'll go to brine draw. Mixture of water and brine is introduced into the distributor tube. Now, you've got a full brine saturation, 100% brine in the brine tank. But if you were to rinse 100% brine through the resin, you wouldn't get a very good, you get ion exchange, but you won't get good capacity. So the injector actually is sized so it can bring in an 8 to 10% brine solution, okay? And when it brings that in, it regenerates the resin as hardness minerals are replaced by the sodium.
I'm just looking at the slide. You know, Corey and Carl, Todd. When you look at the slide, you're feeding in your brine from the top. Okay, so your brine comes in the top of the tank. You see that process of the sodium kicking off the calcium and magnesium. When regeneration is completed, or when brine draw is completed, where would you expect the most regenerated resin to be and the least regenerated resin to be? Ms. Corey, how would you answer that?
I'd expect most of the regenerated resin would be at the top,
That is correct.
because it's getting
That's correct. And you
more
see
bombarded.
the most pure brine, that process of the calcium being kicked off the resin, the calcium is being kicked off that one resin bead in this picture, but that calcium is traveling down to the tank. So you're sending all this calcium, and the calcium is constantly getting kicked off, then reattaching to another bead, and then getting kicked off, and attaching to another bead. So what happens by the end of regeneration, your upper bed is more regenerated than your lower bed. Tom mentions, okay, 2 regenerations back to back. Why? For that reason. You can increase your salt amount. You can add more water to a brine tank and increase your salt amount to get more of the calcium down the drain. Ultimately, by adding more water to your brine tank, you're increasing the length of your regeneration. You're increasing the length of your brine draw, ultimately increasing the length of the time that it sees a higher concentration of salt. What that does is it drives your higher regenerated resin. It becomes lower and lower in the tank because you have a more extended period of time with the brine. And the reason I mentioned that is if you want, again, I don't want to take this away, if you want to hit the button. So, because you have the slow rinse, and keep hitting. Well, I guess I'll let you keep going. But the reason I mentioned that is what wasn't shown in that cycle, that 6th cycle, is Carl. Is Carl here?
Carl here?
No. Okay. Well, you're going to see when you program these, the clack valve especially, you always have a second backwash. What is that for? You know, that's and I want you to maybe talk about. I'll let you keep going with this drop.
We're not,
This
there's
is the next slide. If you want to keep going.
No, I want to talk about this.
Okay, yeah, go talk. But I want you to just keep, because it wasn't shown in your loop. You went right to fast rinse.
Yes.
The majority of the commercial valves that we do now have a second backwash,
The clack.
and I want you to mention that at least. So
Okay.
now that you understand that there's more regenerated at the top
No,
and less at the
continue.
bottom.
Explain this second backwash then.
Okay, well the second backwash, what it does is it redistributes the bed. So you're less regenerated in the bottom, you're more regenerated in the top. So by doing a second backwash, you don't need to backwash the resin for a purpose of, you know, scrubbing the beads and sending debris down the drain. You're backwashing for maybe a couple minutes, maybe 2, 3, 4 minutes, for the purpose of stirring the bed. I just want to get the stuff on the bottom to mix with the stuff on the top. That way, when you go into service again, you have a more consistent quality over the life of the bed. Otherwise, initially you have 2 parts per million. You have awesome water. And then with 100 gallons left, you might have 7 parts per million, which is still soft, but not as good. So what you do by stirring it up, you might get a consistent 3 parts per million over the life of that bed.
Well explained. So now, so here we go to the previous one. Because the drain line is restricted and the flow rate is relatively slow, it will take time after the control has finished drawing brine to completely remove the salt from the tank. That's why it continues to rinse for an extended period of time. But now, you see 3 different salt settings per cubic foot. And they all have, we use them all. We don't just stick with one. The first one is 6 pounds per cubic foot, which is a technique that you'd use more on a residential application on clean water, Appleton City water, Mina water, something like that, because you can see that the brine concentration percentage hovers around 8.5% on the red dot, and the peak, it remains at that peak at a very short period of time, and you can see it starts to drop right away. What happens here, you will get more capacity per pound of salt, but you don't get the high resolution of soft water with it. So like I mentioned earlier, on residential applications, you can get away and really be satisfied with under a grain of hardness, you know, under 17.1 part per million, okay? But then you get into a car wash would be the next one, where you want a higher resolution soft water. You want to be hovering that 2-3 part per million range. So you're going to want to have a higher percentage of brine in your elution study, and hang on to that. I don't have a pointer, but to hang on, have that top line be as long as it is. Okay. 15 pounds per cubic foot is what we would set up for like a boiler application, where we need to maintain consistent 2 part per million or less, preferably 1 part per million or less. And that's the only way you're going to achieve it. You're not going to achieve it by doing it the other ways. Okay? Not permanent, not consistent. Maybe right after the regeneration you'll get it, but not consistent. The red dot indicates the point which the valve stops injecting brine. And what that means is when the brine tank gets sucked dry. If there's an air check inside the brine tank. So let's use the center one for example. At 30 minutes, it took just under 30 minutes for that brine to get all sucked out of the brine tank. Well, that valve still continues to have a vacuum to it, but it stops drawing because the air check seats. If you didn't have an air check in the brine tank, it's going to draw air the whole time, and that creates trouble. So, to make a long story short, it stops drawing brine when the brine is out of the brine tank, the air checks, but it continues to rinse slowly through that bed.
I was gonna ask you, well, I've got a huge water softener. Is that the same curve that I've got for my huge softener as it is for my home softener?
Absolutely. Yes.
I know. I was gonna have you explain that. The time.
Sorry. I thought you were asking a question.
Yeah, no, the timing is the same whether you've got a very large water softener or a small water softener. The reason being is we size the injector and the drain line flow control accordingly. So that's why you'll see some water softeners are drawing at 5 gallons a minute. They actually are literally drawing 5 gallons a minute out of the brine tank. And you've got others that might draw an eighth of a gallon a minute. So a lot of times people are like, well, yeah, my water softener is full of, it failed, my injector. Corey, you're going to get to a lot of sites. My injector failed. It's plugged. My brine tank overflowed. All right, now I got all this water in my tank, John. Should I bail all this salt water out of here, or isn't it going to stay this way? Well, no, because typically you're drawing all your salt out in about 20 minutes or less. So, what does that mean? Well, that means I've got 40 minutes of draw that typically is just slow rinse. Well, if your brine tank is full of water, you're going to draw it all out eventually. Through that first cycle, you might have a little bit of salty water, but that's where your fast rinse comes into play. It'll purge that because you're going to turn that over quickly. You're going to have just a super regeneration ultimately is what's going to happen, is because you're going to draw to concentration and it's going to flatline right at the top because you're going to have such concentrated salt all the way through the brine draw.
That makes sense.
And that's not always a bad thing because if the injector is plugged, it's been a while since they've had soft water anyway. So you're giving them a super regeneration, somewhat eliminating the need for double regeneration.
And here, we go to a slow rinse. When it draws brine and it rinses down through that resin, it's say water from the inlet rinses down through the resin, and this is why we like to sell twins on residential applications where there's cannons or high iron, because the key here is that the water from the inlet rinses down through the resin. Okay, I always say with a single tank softener, I compare it to washing your hands in a mud puddle. If your hands are extremely filthy, you wash them in a mud puddle, they just become less filthy. Okay, same thing with if you have high iron. You regenerate a water softener with high iron water, you're going to always get some iron leakage. When you use a twin, the unit that regenerates with soft iron-free water from the other tank. So you get a truly clean resin bed at the end of the regeneration. So when that unit comes back online, you're going to get good high-resolution, soft iron-free water. Water and any excess brine left in the tank are sent out through the drain. Then here's your second backwash that John explained. It just reverses the flow. Once again, the word that you gotta utilize is it reclassifies the resin. There's a lot of value to reclassifying resin. You get a longer life out of it. You also, by reclassifying it, you get the longer life because you use different exchange sites. Because when it's in service, water is flowing from the top down. And there are some packed bed water softeners out there that don't regenerate. One is the water loss. It never backwashes. Okay? So the same exchange sites are always being introduced with sodium and calcium. Okay? The water's coming down and it always rinses the same direction. And a good way to understand what I'm trying to explain here is this happened about within the last 10 years down by Milwaukee. I was explaining it to Dan. For centuries, the water flowed from the west to the, on the east side of west side of Lake Michigan. The water fed Lake Michigan. The water flowed from the west to the east for centuries. And then we had our drought several years ago, and the water directional flow direction changed. Water actually started to flow from Lake Michigan out into the suburbs. 600 feet down, deep wells. The water was flowing opposite direction. And what happened is for the centuries, water was going this way across these rock formations. And when the water reversed, all that silt and debris that was on the backside of those rock formations got exposed to flow, which they never had flow before. And in essence, it backwashed that off of the rock formations, and it ended up into the community water supplies in the form of arsenic, iron, even cryptosporidium, oddly enough.
Every sulfur backwashes twice?
No.
Just the ones in the boilers or the...
No, or more modern ones. The clacks do. I don't know if the new Freck commercial ones do. We don't use enough of them.
Most of them don't. The reason that clack can do a second backwash and that they use it so often, I think part of it's marketing, but they use DC drives, so their piston can go both directions. So they can go directly to where they want to go, rather than going all the way around. And that's why you'll see that when DC drives are used, that's why they use them, so that way they can move multiple directions by switching polarity. AC is always, it's alternating current, so that you can't switch polarity. It doesn't matter which way you wire it, it's alternating. With DC, you got a positive and a negative. If you switch polarity, ultimately, internally through the controller to the motor, it'll reverse.
Okay, fast rinse. Water from the inlet rinses down into the resin, downflow at a higher rate, and usually fast rinse flow is controlled by the drain line flow control for backwash. So your fast rinse rate usually is the exact same flow rate as your backwash flow rate. Water and any excess brine left in the resin tank are sent out through the drain at that time. And once again, to reiterate, rinsing at a faster flow rate helps to pack the resin bed to result in a more even exchange. And that can last anywhere from 1 to 10 minutes. That's a programmable function. And then fill, or some people call it refill, same thing. Water from the inlet rinses through the resin to create soft water. And once again, on a twin tank system, the softeners or the brine tank refills with soft water as well. So you keep your injectors cleaner, you keep your brine tank cleaner. A predetermined amount of water fills the brine tank. Water from the inlet rinses through the resin to create soft water. Let's see here. Where am I here? Make it look right, Dan. Let's see here. Pardon?
That's right.
Okay.
Ultimately what it's showing is that your water comes in your inlet, your outlet is still closed, it comes up your distributor, but it diverts the water, ultimately that would be for your outlet, to your brine tank, so ultimately giving you a soft water refill, rather than a hard water refill. If you had a hard water refill, you run the potential of getting more buildup and hardness deposits actually in your brine tank.
And here's one we added yesterday. 1 gallon of water dissolves 3 pounds of salt. Note, systems with salt grid / platforms require more time to dissolve salt. That's key to remember. You don't have as much, when you don't have a salt grid, your salt's sitting right down inside of, in the water, so all the water is surrounded by salt crystals. You're gonna create a saturated brine extremely fast. Versus when you have a salt grid, a salt platform, it takes a significant amount of time to create a full, to saturate all the water below that grid with salt.
Is that true?
Yes, very much so.
Because I know
Because you are only saturating approximately 1 inch, usually have approximately 1 inch of water over the salt grid.
Mhm.
So what happens is you're only dissolving 1 inch making 1 inch of brine at a time, okay? And where this run creates a real issue is on high volume twin tank systems. And the reason for that is there are applications where a lot of people will put in a twin tank water softener on a commercial application, not only to get that round the clock soft water. So what they think is, well, I'm going to size it for that it just gives me the minimum amount so I can get the flow through it. Well, then they ignore the capacity. So when they think, well, I don't care what the capacity is, because when one softener is done regenerating, when one's in regeneration, the other's online. So it shouldn't matter to me. But what happens is, in some of these high volume applications, and I've had this happen multiple times, where that softener that is online while the other unit's in regeneration will become exhausted while the other unit's regenerating. So what happens, as soon as the unit gets done regenerating, the other one goes into regeneration. And if you have one brine tank and there's a salt grid in there, you gotta remember, the last step of regeneration is brine refill. So it refills for, let's say, 10 minutes, puts fresh water in that brine tank, and then it goes into the service position, and instantly that other unit goes into regeneration. Backwashes for 10 minutes. So really in about 15 minutes time, it's gonna be drawing brine again. That's not enough time to create brine. So it becomes an anemic regeneration, and you run into hard water. This is interesting. Dan did do a good job on this. Salt dosing unit, pounds of salt per cubic foot of resin, and common range for most softeners is 6 to 15 pounds per cubic foot. That is the most common. So you see, once again, it kind of reiterates what we showed before, but it also displays. We should print this out too for the guys. You can carry this one. This would be a good one.
This whole slideshow would be good to carry with you.
Yeah.
Show this to a customer if you want to do.
Yeah. So you can see with when we regenerate with 6 pounds per cubic foot, you're going to expect just under 17 part per million of hardness, just under 1 grain. When you regenerate with 10 pounds per cubic foot, you can expect just under 5 parts per million. And when you regenerate with 15 pounds per cubic foot, you can expect 2 parts per million.
And one thing that you can keep in mind when you're looking at this, if you look at it from a capacity standpoint, you go, well, why don't we always do 6? It's much more efficient. Well, the bottom number is what really is affected, is your quality. Now, the flip side of that is you get plenty of customers that are asking you, oh, I hate soft water. I don't want it to be as soft. Can you turn it down? We always say, no, you can't. And soft water is soft water. Kind of just, we try to teach them what soft water is ultimately. But the reality is yes, you can. You can turn it down. And consistently turn it down. You don't have to put a blending valve in necessarily. You can do, you're not going to be able to make it 2 grains hard necessarily. But you can adjust your salting. You can adjust your salting. So, for example, on a Reliant, take it from standard to low. What's that going to do? It's going to increase the efficiency, but it's going to decrease the quality. So the quality is going to get worse, but the efficiency is going to go up. At the end of the day, what is that going to provide the customer? Well, it's going to give them about 1 grain hardness. But for the person that doesn't like that slippery feeling, that might be just enough to take them from 5 parts per million to 17 parts per million. It might be just enough to make them go, you know what, I can tolerate this.
And that would, I'm assuming, also mean that they're using less salt.
Correct. They would use
So
less
they might
salt.
like that too.
Right. Again, and that's, we try not to focus too much on the salt, you try to focus on results.
Mm-hmm.
If the results are that they want are 17 parts per million, not 5, they don't care about the salt. They're focused on the results, and I think that, often we worry too much about other people's salt usage. If they want 2 parts per million, crank her up, baby. It doesn't bother us.
Mm-hmm.
If that's the results they want. If they want 17 parts per million, because, the husband doesn't like soft water and the wife does, there's a compromise right there. It's not going to give them awful water. It's just going to give them.
The only caution to remember on that is you can play those games I shouldn't call it a game, but you can make those types of adjustments when you're dealing with hard water.
Yes.
If they have iron in the water, don't consider those type of adjustments.
Yeah.
You actually got to consider the other way. You got to go more rich on your brining and more frequent.
And that is one challenge that we do run into is, a lot of times you can have that conversation, but at the end of the day, it's, are you going to tolerate steaming again? Well, no, well, that, you don't have those options.
Right. Here we go. This is a model number DCS6-300-150. It could either be a single tank or a twin tank. This softener contains 10 cubic feet of resin in the vessel, in the pressure vessel. I love that song. Anyways, common range for most softeners, again, is 6 to 15 pounds per cubic foot. Salt types, there are many different types of salt. Higher purity is better. Look for, if a customer asks you, if you don't buy your salt, let's say you're selling somebody, working with somebody out in Wausau. No, we don't deliver salt out there. They say, well, what should I buy? Just look for salt that's close to 100% water soluble. Types, you got the iron inhibitor salt, which is the best, even without iron. It's still a highly recommended salt. Then your better type of salt is the pellet. And the reason why we say that solar is good, because our solar is the same purity as our pellet. Okay? The reason across the board we have to say solar is good, because it can be yellow or impure based on its source. A lot of the solar salt that's sold throughout the country is ocean salt. It's as impure as rock salt. It's got up to 2% impurity. So for every 100 pounds of salt that you use, you got 2 pounds of dirt in the brine tank. Not ours. What is ours? Ours is 99.9. Six?
99.6% pure,
Yeah.
99.9% water solid.
Water solid.
Probably, yeah.
99.6% pure? Okay. Problems with low quality salt? Ridging and caking, clogged air checks, and clogged the pickup valves. And you can also damage resin. You think, well, how can dirt damage resin? The dirt doesn't. If the dirt in the salt is just going to cause problems with the control and plugging your brine tank if you use rock salt. It's not going to hurt the resin. The type of salt that's going to hurt resin is, and it's not even mentioned on here, is block salt.
I had somebody came in the other day, still use block. I hadn't heard that for years.
Yep. And if you ever see open up a brine tank where there's block in it, you'll see there's almost a foamy scum on the top of the water floating. And that's because to adhere to construct block salt, they use 2 products. They use coconut oil to keep it from sticking to the forms, and then they use a glue, it's a binder, to hold it into that block form. And that will actually coat your resin beads, get into the exchange sites, and shorten your capacity, so it will hurt your resin. So if you've got see somebody using black salt, I would advise them discontinuing it, clean the brine tank, and start out with a good, clean diamond salt product.
Quick question, so the pellet salt you said is better than like the crystals. Why is that? Is it because of the sourcing or how it's produced?
Not ours. Our
Right.
pellet, right.
Yep.
But the pellet salt is actually a processed salt. They actually will break the salt down. Some places they actually, in most places they dissolve it, and they filter it, they skim it, they separate any dirt from it, and then they that's why pellet salt's more expensive, is because they have to re-evaporate it.
Gotcha.
And then compress it into these pellets, which is an art in itself. Because if you compress it when it's too warm, you get too soft of a pellet, and you get mushing in the brine tanks. If you compress it when it's too cold, it falls apart. It dissolves, but it just falls apart in the bag. So, who would have thought that there's a lot of science to salt? Here's interesting.
Ryan's got a question.
Could I ask why you wouldn't want it to fall apart in the bag? I mean, it seems like that would make more surface area and more efficient salt.
Because it sits for long periods of time in the brine tank. Remember, you only got a foot of water in the brine tank approximately,
Right.
and you've got 3 feet of salt over the top of it, dry salt,
Okay.
and whatever becomes wet is going to become compressible. So that weight above it is going to compress it. You're going to have one massive cake of salt on there that water can't penetrate.
Oh, okay.
So then you get a brine tank overflow problems. When the water gets mushed, or salt gets mushed at the bottom of the brine tank, the water will stand on top of it, but the softener is still going to refill. So it refills the brine tank, and the water stands on top of that whole much salt, and it's going to overflow.
So what you're doing essentially is creating little channels for the water to go in and...
Yes. You want to keep it as porous as possible.
Okay.
But also, the finer the salt, the more displacement you get. And this is, let's see here. We should mention, I think we need to change this to explain that this is displacement caused by brine or by salt. Right? Brine alone can expand your water by 12%. Because you got to remember, a gallon of water dissolves 3 pounds of salt. A gallon of brine houses 2.66 pounds of salt. Okay? So if you want to have 3 pounds of brine, you're going to have over a gallon of water, over a gallon of brine. So that's displacement. There's actually going to be some expanding of the solution. Another thing to remember is brine in salt can expand by 50%. Actually, water. So let's say you put, we should change that, water in salt will expand by 50%. I think we gotta learn that.
Put 50 to 80. The
Yes.
reason I say that is because we did our own test with the solar, and it was over 80%. We did that with lowering. We compared the pellet to the solar because a lot of commercial customers were having overflows. And this exact thing happened the other day on the phone. The customer called me, said, John, he's like, our software just started overflowing, consistently. Oh, okay. Like, has anything changed? Did you change your salt product? Well, yeah, we just went from a pellet to a crystal. Like, that's why your water stopping or your brine tank's overflowing, is your displacement is significantly more. Because it was consistently spurting out maybe a half gallon of water on the floor. It wasn't significant, it was just a little bit of water. It was just enough to push it up over that limit because their displacement was heavy, or was higher.
You know what I mean by displacement, Eric? Because does anybody have a question on that?
I think I kind of get the idea of what's going on. Maybe you can correct me on it, but it basically like the salt is, since the salt itself is taking up some volume, it's expanding it outward.
Yes.
We did an experiment actually where it's kind of like the opposite effect when I was in college, where we had to mix water and ethanol together. And interestingly enough, some of the ethanol fits into the holes that are left in the water molecules. And so if you mix, a liter of water with a liter of ethanol, you get slightly less than 2 liters of solution.
Oh, really?
Because it fits together a little bit more efficiently than just pure water molecules will fit together. Not much, but a little bit.
And so also just to take it a step further with this, is it true then, just, I'm not sure if I'm understanding, with the brine tank, if you fill it full with salt crystals, is there going to be a higher chance of overflowing than if you fill it full with pellets? Or no? Does that not make a difference?
Your displacement is higher with salt crystals, so if your water level is high with salt pellets, your likelihood of overflowing with crystals is higher than with pellets.
Yeah.
Because pellets are about 50% displacement, crystals are about 80.
Gotcha.
I forgot about that test that you and I did, and I think that we should make a note to change that.
That's why a grid is used. Because a grid, you take that variable and you say, yep, goodbye, I don't care what you're using, the variable's gone for displacement, because even if you're 100%, if you're only an inch above the grid, who cares?
It says, you're playing minuscule amounts.
So is it just that one is being absorbed much more quickly?
Just they fit together, the salt crystals just fit together that much
They're
tighter.
smaller. They're just smaller pebbles versus big pellets. So you have more void in pellets. You've got larger voids between the pellets.
Okay.
Versus the crystals, you have much smaller voids.
So how to correct the issue other than changing salt, do you change the amount of water?
Nope. If you change the amount of water, you're going to dissolve a different amount of salt. So if you that's what a lot of people want to do is, that's what a lot of people call them. They say, oh, we turned the brine down. Well, you're not going to get soft water anymore either.
That's right.
So to solve that problem.
You got to remember, it's a fixed amount. I mean, a gallon of water will dissolve 3 pounds of salt. It's not selective as to if it's rock salt, solar salt, granulated salt. It doesn't matter. A gallon of water will dissolve 3 pounds of salt.
Mm-hmm. And then that's where, the good recommendation, because I actually had this conversation a couple weeks ago with another guy, their salt grid collapsed. He's like, oh yeah, it collapsed a couple years ago, cleaned down, and I built my own out of masonite. And I guess that's what was originally in there. But he's like, I just went to Menards and got pegboard and double layered it up. I'm like, that's fine if you want to make your own grid. I'm like, you can buy one from us. But he's like, I got one quoting, it was like $900. He's like, I made this for 30. I'm like, I tell you what, if you want to make your own, by all means, knock your socks off. You don't need a million holes in it to get the water through. You just need a couple holes. And what ended up happening is, when it collapses, water level shot up. So the cheapest solution is either go to a pellet, which is more expensive for most people, and if you're using high volumes, it just doesn't make a lot of sense. So if you get the same quality product, look at the blue to our green, there's over $1 savings. Well, if you're using, 18 pallets a month, there's a savings to go with the green. Well, what are the options? If you spend that $900 on a grid, or whatever it costs you on a grid, get that water, get something that's going to support your salt up there. You can use whatever salt product you want, and you're not going to run into those kind of issues. And that's usually the recommendation is, hey, guy on the phone, my recommendation is clean your brine tank out, pop a grid in there, and you can use whatever you want. And
all of a sudden that $900 is after a couple of months is getting you savings. You take a look at like Marion Pilot. They're going through a semi-load every other week.
And not just from us, I mean, we've got another source, so probably a couple of months for free.
So that's, again, it's not always $900 bucks. I mean, a salt grid, that's why we standardize on most of our softeners to have a salt grid when we sell them. Why? Frankly, we just want to eliminate the call for overflow or based on the salt product they're using. We don't control the salt product, so the one way for us to control the phone calls and not getting them is to put a salt grid in them, so that way you can use rock salt, and at least we're not getting the overflow calls.
All right, move along, regeneration initiation. You have manual. This is, you do see them out there every once in a while. And commercially, operator initiates a regeneration, that's the only way it regenerates. Time clock, where the software regenerates at a set time or duration. Example, regeneration at 2 a.m. every other day. Some time clocks are like that. Then you've got a meter, which is also considered demand regeneration. The software measures flow rate. Not flow rate, it can measure flow rate, but flow volume. You should change that. It measures flow. And regenerates after a volume of water has been treated. Most efficient, uses uses all capacity.
Because it doesn't use all capacity,
No, it
right?
doesn't.
Yeah.
No.
It doesn't say this X amount.
But usually,
Well, let's just call
yes,
it more
leave it that way, because it uses all program capacity.
If you say, most efficient uses all program capacity, that would be best. Yeah. Then you got meter demand and time clock, which most of our controls offer. You can set it to be meter initiated with the calendar day override, and there's multiple reasons for using an override. For like even tannin applications in a cottage, it's good to refresh that bed even if they're not using the water regularly. Even if they don't use let's say it's set for 1,000 gallons between regenerations. If they're not up there but every 4 weeks, you want that thing to regenerate maybe every 10 days. It's important to refresh the bed. Also, if it's we do sell equipment that's going into Arizona and Florida and warm weather climates, outdoor applications, you want to keep the bugs from growing inside a resin bag. So there's multiple reasons why you would set a software with the D override. Then there's external relay, which is an electronic signal from an external source that's used for industrial purposes. And then, last but not least, I think keeping a daily log for our commercial customers, we should provide this. We should carry them on our trucks and encourage our commercial customers to keep a daily log of the water softener's performance. It helps to pinpoint problems. It really does. I know in our car washes, we kept a daily log. And you tell what units online, and how much capacity is remaining when you generate it, or excuse me, when you test the water, and it tells a story. And you can come in on a boiler application and see a log. You can see the history. You can almost tell what's wrong with that softener without even touching the softener. There you go. Thank you for listening. Any questions? Yes.
I do have one. You mentioned that you put calcium down, you mentioned, I'm getting ahead of myself. You mentioned that you put gravel down in the bottom of a softener, correct?
Yes.
Isn't gravel mostly made of calcium?
We use a quartz.
Okay.
Good question. It's a washed quartz.
Okay.
So there's nothing, no sloughing off of any. It's a washed quartz. So it's you can get quartz at a local quarry here, but it's not washed.
Okay.
In an example of why we use what we use, yesterday I got yesterday morning, got a call from a guy doing a carbon rebed. They had carbon, they rebed their carbon filter, and he didn't have gravel. He didn't buy any gravel when they ordered the carbon. And he knew enough that he needed gravel, so he went to a local Lowe's or whatever it was and got gravel there. Got, pea gravel or something of that nature. And he put it into whatever he got for gravel. He poured it in, poured the carbon on top, started running it, and a few minutes later he had no flow. So he dumped it out, and he realized that not only was the gravel that he got not washed, but when he went like this, it flaked.
It's a classic example
it broke
of
down.
penny wise, dollar foolish.
It broke down, and he did what he thought. Everyone pours it. You pour that gravel in 1,000 times, and you don't think twice that it's a special gravel, which is not anything special. It's just there's a reason that we use what we use.
Okay. So it was plugging up.
It was ultimately the fines were plugging up the slots on the distributor, because it wasn't like you get the distributor out, pour water through it, and it wasn't like it was plugged up. But because that was sloughing off, it was just that all those fines were packing tight down in the bottom of that bed and just not allowing any flow through, or very minimal flow through.
Cool.
Yeah.